All right, perfect. Okay, then I guess I'll just start with a brief introduction. So, hello everyone. My name is Carlo Refice. I am currently a master's student in computer science at EPFL in Switzerland. Last semester, I was a research intern with Oracle Labs in Zurich. I worked with the Graal VM team, specifically on the Graal compiler, and they mostly worked on improvements in compilation time. And today I wanted to talk about one of the features I worked on during my time at Oracle Labs, and that is quick build mode for a native image. Now, Christian already gave a very in-depth explanation of the internal workings of a native image. So I don't feel too much of a need to repeat that, but I still wanted to give a sort of very high level brief introduction into the native image build process. So yes, native image, its purpose, once again, at a very high level, it tries to compile a Java executable, Java application to a native executable called image ahead of time for a number of improvements, performance obviously being one of them. And the native image build process, it typically takes up these steps, as you can see here. So it starts from a reachability analysis, which is a static analysis where the call graph is analyzed to determine which methods are reachable during program execution. Then those methods are parsed, and some inlining is performed as a sort of pre-optimization before the actual compilation is performed. And the compilation, is actually done by the Graal compiler. So after the compiler outputs executable code that is then packaged during the image generation process, it is packaged into an executable along with the minimal runtime called the substrate VM, which Christian also mentioned. And the improvements I described today all happen in method compilation within the Graal compiler. So let's drill down a bit. I also give a very brief overview of how the Graal compiler works internally. Specifically, I will focus on the front end of the compiler, although much of what I will be talking about today also extends to the back end in a similar way. So the front end of the Graal compiler uses a custom intermediate representation based on the sea of nodes model, which it's essentially a graph-based representation where each individual value and operation is represented as a node in this graph, and then the edges between the nodes represent the dependencies between the values. And this graph undergoes a lot of transformation during the compilation process through what are called transformation phases. So each transformation phase represents one specific transformation operation that we want to apply on the graph. And these operations are grouped into three major tiers. There is the high tier, the mid tier, and the low tier. And each of these sort of expects some invariance to hold true in the graph as it is. So for example, in the high tier, we will have some high level constructs, such as exception throwing that is represented as an individual node. And in lower tiers, we will have that sort of be broken up into, for example, an if statement and a de-optimization node that then will actually unwind the stack. These sort of transformations are all collectively are known as lowering, and it is in general performed between each tier. Now here we can see which compilation phases are actually performed at each tier, at least with the default compilation settings. As you can see, there are quite a lot of them, but not all of them are created equal. Some of these phases are transformations. So as I mentioned earlier, they can be considered a part of lowering. And these transformations are actually necessary to compile a program at all with Graal. Since, as I said, the compiler expects different invariants to hold off the graph at different points in the compilation process. And the other optimizations other phases are instead purely optimization phases, whose sole purpose is to improve program runtime or memory use or some other characteristic of the program. And here I have highlighted in white which phases out of the phase plan are those that are actually necessary to complete compilation. And as you can see, they make up quite a small part of the overall phase plan. And not just that, but they also take up a minority of the time spent during compilation, slightly less than half of the time. And so the thing is that there are instances where it might not be necessary or even desired to run the full optimization suite. And for those instances, the Graal compiler has what is called the economy phase plan that presents a more streamlined phase plan. Only the necessary phases are applied. And that is done in an attempt to trade off quicker compilation times for a slower program at runtime. This is already used in Truffle. Truffle, kind of like Java, also presents a multi-tier compilation model where economy mode represents the first sort of highest tier of compilation. And it could potentially be used, like it could be seen as a sort of replacement for the C1 compiler in the hotspot Java tier, the compilation model. However, it needs to be noted that the C1 also does profiling of the generated code, which at the moment is not implemented in the economy phase plan. Right, so to give a bit of a concrete example of how sort of optimization is impacted by these different phase plans, here we have an example program. It's a very simple program. So essentially what it does is it takes in an input argument and essentially through a redundant loop checks if the argument is equal to 1. If so, it returns true. And if not, it will essentially, through some obfuscation, go through the remaining 9 iterations of this loop and then exit it and return false. And so here we can see that the first iteration is really the only relevant one for program execution, because no matter what, once the first iteration completes, all the others will then also have to run, and then the only real side effect that will be caused is the loop exiting and false being returned. And so with the default phase plan features more expensive optimization phases. In this case, I believe that loop peeling is the one that is the most responsible for this transformation. It will sort of recognize exactly what I said about the rest of the loop being irrelevant, and will perform very wide transformations of the program, and it will such that the program is then reduced to a simple branch. It's just a simple if check with a conditional and then a return. This obviously doesn't happen in economy mode due to the many missing optimizations. And so the original program structure is preserved, which results obviously in a lot more nodes and also obviously a very significantly slower runtime. Now let's go back to the native image build process. So out of all the phases that are needed to build an image, compilation is by far the one phase that takes the longest out of all of them. These particular numbers were obtained through bootstrapping the Graal compiler using native image. But this same pattern holds with the other programs where we see that method compilation is consistently the part of the build step that takes the longest. And as of yet, the compilation in native image was always performed with the full phase plan. So there was little way to choose between whether we wanted a higher optimization level or a faster compilation. And during development, for example, when multiple builds are done in quick succession, or for example, during CI, where quicker builds are desirable, the user would benefit from being able to choose between the two. And so that is exactly the idea of the quick build mode, wherein the whole image is compiled with economy mode. And the way for the user to enable it is through just a simple flag passed at the native image executable on the command line, OB, which stands for optimize for build time. I have to stress that this mode is intended as development focus mode, and it should not be used for deployment, since, as I mentioned, many optimizations are disabled, which can significantly impact program runtime. Now, in terms of implementation details, it might seem like integrating economy mode in a native image was just a simple matter. But there was one significant challenge with it, and that is the fact that the native image build process is essentially configured through what can be seen as global variables. They're singletons that are shared between the build step, so what we call the hosted side, and the actual program at runtime, so either the substrate VM or the actual code. And with most programs, that does not pose a significant problem. The program is mostly not interested in sort of the flags that were used to build it. But one instance that is special is that of libgraal. And libgraal, for those that are not familiar, is essentially the precompiled native image of the Graal compiler. So this is what I was referring to earlier. It is essentially an extended form of bootstrapping where we compile the Graal VM compiler with native image that uses the Graal VM compiler to build it. And it just so happened that some of these global flags that are used to determine the phase plan of the image, the phase plan used by the compiler for the image that is being built. But these flags also dictate then for the libgraal image, which the phase plan of the compiler at runtime. And so this is sort of hard to wrap my head around, but most importantly, we don't want the image features to be influenced by the way in which the image was built. And so we needed a fix for this for the implementation. Thankfully, as is the case with many other things in this field, the solution was to add an extra layer of indirection between the hosted compiler configuration and the runtime compiler configuration, such that they can both be changed and adjusted independently. Okay, so with this, I'm sure you all wanted to see some numbers. And so here they are. In this and the following slides, I'll show quickly some benchmark results that I obtained with the da capo and the Scala da capo benchmarks in particular. And here we have a comparison of the compilation time with the default and the new OB flag. And as you can see, the compilation step now takes less than half as long as it did as it does with the default flag, with the default compiler configuration, where the overall image build time is reduced by a bit more than a quarter. And if we drill down into the results for each benchmark, we can see that the overall improvements in build time are very consistent. Sort of there are no obvious sore spots or bottlenecks in any of the benchmarks. Now, of course, as I mentioned many times now, the program runtime is affected by this mode. And we found that on average, performance was around twice as slow with quick build mode than with the default mode. However, these results were not as consistent as compared to the compile time ones. There were some benchmarks which performed only a little bit worse than the default one, and some that performed very significantly worse. However, I invite you to take this chart here with a grain of salt, as these runtime numbers might change in the future. And in fact, I'm mentioning this because they already have, because since I collected the data, some work has been performed on identifying exactly what the bottleneck for some of these benchmarks were. In this case, if I remember correctly, it had to do with inlining not being performed as much as it should be, and that was an extreme bottleneck for specific instances. So that has already been fixed, and so these numbers are prone to change. Finally, looking at the space impact of this mode, it is quite reasonable. We found around an 11% decrease in the size of the generated image, which is also due to, as I mentioned, the reduced inlining, which makes the code smaller since it is not copied around in the executable as much. Whereas the memory footprint, that is the maximum resident set size, so the amount of memory that is actually used by the program at maximum, has increased by around a quarter. And once again, this is a result of the fewer performed optimizations, such that not as many constructions and the usages of memory can be optimized away. So in conclusion, I would say we're successful in giving the user an option to choose for reduced compilation time, but there are still improvements to be made elsewhere in the native image build process. For example, in the analysis stage, we could use a faster, less precise algorithm. And as I mentioned, there is some tweaking ongoing to reduce bottlenecks in certain benchmarks and sort of to try to find a sweet spot between runtime and compile time, of course, in a way that prioritizes compile time for this mode specifically. And once all of that will be sorted, then a quick build mode could potentially be enabled by default, sort of making it more like other compilers nowadays that in the way that higher optimization levels are sort of requested on demand rather than enabled by default. Okay, thank you for listening. That was about what I had to say on this topic. I will now take any questions if there are any. I see. Oh, Great. I see a question in the chat. How does dev mode runtime compare to hotspot per Graal or C2 JIT, or is that not relevant to the dev mode use case? By hotspot plus Graal, as far as I know, I did not obtain this data. Maybe Christian has some input on this. But for the time I was there, we did not take this benchmark. Yeah, so unfortunately I can't really answer that question. Okay. Can everyone still hear me?
Yeah, do we have any other questions from anyone?
You mean if I have?
Oh no, do we have questions from anyone else in the audience?
Yeah, sorry, this is Uma. I have a lot of background noise, so I was keeping myself on mute. But I'm not sure I understood that slide you talked about with respect to libgraal. What is the relationship between this dev mode and libgraal? Is one dependent on the other, or is it possible to, use this build mode and not use libgraal?
Yes. So it is absolutely possible to use this dev mode, this quick build mode without libgraal. It is a sort of generic build mode that can be used for any native image that one can generate. It's just that libgraal acted as a good sort of stress test for this mode because the code base of Graal is quite large, and as I mentioned, because it is a sort of bootstrapping test, there were a lot of specific challenges with libgraal. But the two are sort of independent. It's just that quick build mode can be used to build libgraal. That's as far as the relationship goes.
Yeah, to jump in here, it's like libgraal is very interesting use case because when you build libgraal, you use Graal as an AOT compiler to compile Graal to be used as a just-in-time compiler. So it's like the code that produces the image is the same code that it's also put into the image. And it's like, that's very nice, but you need to make sure, of course, that these two things are completely independent, because it's like, just because you want to use a quick build mode to build libgraal, you don't want to put a less optimized version of Graal into libgraal itself, so that Graal actually, so when libgraal runs, that it produces slower code. It's like, it's the same like with the native images when you put it in as a JIT compiler for truffle JIT compilation. It's like you use the same JIT compiler to AOT compile and put it also into the image. And these are completely independent configurations of Graal. And in theory, but in practice, you need to be careful that they are really independent.
Yeah, understood. So it'll be interesting to see if something like this can be done, although, we already have tiered compilation, but, for the non-native image scenario that Nick asked about. So, all right. Any other questions from the audience? I don't see any on chat, so let's thank the speaker. Thank you, Carlo, for presenting this work. It's interesting, and we look forward to seeing how it gets developed further. So,
thank you very much.
Thank you.